Hello my dear students, welcome to IMS GATE Academy. Good evening and namaskar. I am Vipin Mishra, the lead mentor at IMS GATE Academy, and you are watching the most expected concept series of IMS GATE Academy. Now in this series I am discussing the subject, a conceptual and a very important subject for all electrical aspirants, that is none other than but the power electronics. And this is going to be the third lecture. This is going to be the third lecture of this series. In this lecture, I am going to discuss about BuckBoost Converter. One such topic which is surely going to give you a gate question. Okay, so you are going to have a gate question. Surely you are going to have a gate question from this particular topic, BuckBoost Converter. So let's get started and discuss BuckBoost Converter. So what we have seen earlier in the lecture 1, we have seen Buck Converter. If available supply is fixed DC and we want to have a DC of lower level, then we will use Buck Converter. If available supply is fixed and we want to have a DC voltage of higher level, we will use Boost Converter. So in order to step on or step down or step up the available DC fixed voltage, we need to either step it down or step it up, and we need separate converter for that. Now BuckBoost Converter is one such solution which will enable both the things at one go only. Thank you Sandeep sir. So BuckBoost Converter is one such converter which will enable you to go with only one converter, and what you will do, through this one converter you will be able to step down the voltage and you will be able to step up the voltage as well. Okay, so BuckBoost Converter is a versatile solution if you really want to convert one level of DC into the other level of DC. Okay, so let's get started. So as you know, this is going to be the third lecture of this series. We have completed Buck Converter, Boost Converter. Now it is time for BuckBoost Converter. Okay, so you people have enjoyed lecture 1 and lecture 2 a lot. The same experience I will be giving you in this lecture as well. So BuckBoost Converter, and this is the schedule. You can see total 10 lectures I am going to take here, and all these 10 lectures, in all those 10 lectures I will be discussing 10 important topics. Okay, so you can come here and you can have a better preparation of gate. Okay, so today we are going to discuss BuckBoost Converter. Now what is this BuckBoost Converter? Just a second, what is this BuckBoost Converter? So as you know that Buck Converter can only step down and Boost Converter can only step up. We have a circuit, we have a solution which can do the both tasks. Means we have BuckBoost Converter. So if the available supply is fixed DC and you want to have a voltage greater than the available supply, means you want to step it up, you want to boost the voltage, that is also possible here. And if suppose you want to have a voltage lower than the available supply, that is also possible here. Okay, so you can either boost the voltage or you can either buck or step down the voltage as well. So both the solutions are here. Okay, now why do we need this? Because a lot of applications are there, like solar panel. The voltage that we are getting from solar panel is very low, so we need to step it up. So for that we need Boost Converter. Satellite communication. Now in this we need both type of converters. We need to buck the voltage as well. We need to step down the available DC voltage. We need to step it up as well. Okay, so both types of applications are there. Similarly, we have hybrid electric vehicles as well. So in electrical vehicle also we need that particular type of variety, in which in order to supply the accessories we need to step down the voltage, and in order to supply the motor we need to step up the voltage. For that purpose we also need BuckBoost converters, and none other, last but not the least, home appliances. There are a lot of home appliances that runs on battery. Okay, so inside them we have DC battery whose speed we have to control. By controlling the speed of that DC motor, we will be controlling the operation of the particular device, and this is possible by having a particular converter which can vary the input DC voltage, and that will be achieved by BuckBoost converters. Okay, so this is why we are here to discuss BuckBoost converters. Now what is a BuckBoost converter? Now we have a different type of circuit for BuckBoost converter, and what is that circuit? Just let me just draw the circuit. So first of all we will be having a fixed DC voltage. So first of all we will have a fixed DC voltage whom we want to either step up or step down, and after that what we will be having is first of all we will have a fixed DC voltage, and then there will be a switch on the source side right now, okay, and we will be having an inductor in middle of both the input and output circuit. Earlier what we have seen in buck converter, the inductor was there at the output side. In boost converter, the inductor was there at the input side. Now in buck boost converter, inductor will be in middle of both the sides, and then we have a diode which will connect the load and source or disconnect the load and source, and then finally we have a capacitor here, and after the capacitor there will be a load where the variable DC is required. So here we want to have the variable DC V0, okay, and the polarity of the voltage for this converter will be like this. Lower I am taking as positive and upper as negative. We can take both as well, okay. Rakesh Balchandra, good evening Rakesh, welcome to IMS GATE Academy. So polarity of voltage can be both, okay, it depends. Now we have here the load RL, we have this C, current will now be flowing in this direction, okay, and assume to be positive. It is, if it is flowing in this direction, this is the diode that we have, and this one is the inductor that we have. Inductor polarity is taken positive if it is in this direction, and inductor current will be treated as positive if it is flowing in this direction. This is the switch that we have, okay, this is the switch that we have, and this is the DC voltage that we have. This is the source current, and here it will be the switch current, okay. So this is the circuit that we have, and this will be my diode current. So all these parameters we have in this circuit, and this is the circuit diagram of a buck boost converter. All you need to practice, all you need to memorize, all you need to remember is just this circuit diagram, and rest of the things we will be able to analyze very easily, and we have seen that in buck converter and boost converter, okay. So these are the parameters that we have, okay, and we will be finding each one of them one by one, okay. So switch is present at the source side, low inductor is now connected in between the input and output side. In buck converter, inductor was there at output side. In boost converter, inductor was there at the input side, okay. Now we have a different type of circuit. So this circuit is known as buck boost converter. Now it will be giving us both type of voltages. It will give us either the step down voltage, or it will also provide us the step up voltage as well. Now how it is going to do that particular task, that we are going to discuss, okay. So this is the circuit diagram. Now let us discuss what are the important assumptions, okay. So what are the important assumptions under which this circuit will operate? So the first assumptions that we have is, all the components of the circuit are ideal, okay. So we have assumed that all the components of the circuit are ideal. If we are assuming that all the components of the circuit are ideal, that means input power is equals to output power, or there are no losses, okay. So this is the assumptions that we have taken. Ideally this will not be the case, there are some losses that will be happening in the circuit. Apart from that, we have a very important assumption related to the inductor current. And what is that? The inductor current is assumed to be continuous and periodic. Inductor current is assumed to be continuous and periodic, okay. So what we have assumed here is that inductor current will be varying periodically, and the inductor current is continuous also. For discontinuous inductor current, we will have a separate discussion, okay. So I am introducing the buck boost converter right now in this lecture. So for continuous mode we will be discussing the operation. For discontinuous mode we will have another lecture, okay. So continuous and periodic, inductor current is assumed to be continuous and periodic. Periodic means whatever is the value of inductor current at the starting, after one cycle it is having the same value. Okay. So if this is so, if inductor current is varying in this fashion, what we have seen in all the converter, and that will be true here as well in power electronics, VL average will be 0. Okay. If inductor current is varying periodically, the average inductor current voltage will be 0. Another important assumption that we have is related to the capacitor current or the capacitor. So what we have assumed here, the capacitor, or we have to say that the average capacitor current is 0. Okay. The average capacitor current is 0. Okay. The average capacitor current will be 0, means IC average that we will be having is 0. Okay. So in inductor, the inductor current varies periodically and average inductor voltage is found to be 0. In capacitor, the capacitor voltage will be varying periodically and average capacitor current will be 0. So these are the properties related to inductor and capacitor that we will be utilizing here. After that, we have another important assumption, and that is the capacitor is assumed to be very high. So that ripples in output voltage can be minimized. Ripples in output voltage can be minimized. So we will be discussing the operation of this converter under these circumstances. Okay, so these are the important assumptions that we have assumed related to inductor, related to capacitor, related to the devices, isn't it? So all these are the important assumptions under which we will discuss the operation of this circuit. So let's discuss the operation of this circuit. So let me tell you what will happen during the on condition. Okay, so what will happen during the on time? So during the on time means there are two switches in this circuit. Okay, one is the switch and other one is the diode, and any one of them will be conducting at a time. So on period means the switch is turned on and diode at that time will be in off position. Off time means the switch will be in the off position and diode will be conducting. Both cannot conduct simultaneously. Okay, the type of connection that we are having, both cannot conduct simultaneously. So either the diode will be conducting or switch will be conducting, or switch will be conducting or diode will be conducting. When switch is conducting, that time is called as on time. So on time means the switch will be in the on state. So let's see what will happen if the switch is in the on state. So I am turning the switch to be in on state, and during that time what will happen? Just see, when the switch is on, at that time the diode will be off. So diode I am putting in off position and switch is turned on. So this is the condition that we have in this circuit right now. Just see, this is the condition in which the circuit is operating right now. So this is the output voltage, this is the output current, this is the capacitor current. Okay, inductor polarity is this right now, and this is the beginning polarity of the inductor. Inductor current right now is flowing in this direction, and you can see this polarity of inductor voltage is keeping this diode in off position as well, isn't it? So diode is right now off. This is the switch which we have held in on position. So this is the source voltage, this is the source current, this is the switch current that we have. So all these are the currents in this circuit. Okay, now the switch is on and diode is off. Now what will happen in this circuit? So as you can see, load and source are disconnected. Yes or no? The load and source are disconnected right now. Now I0 has to be maintained constant. So who is going to do this task? Capacitor. Capacitor will maintain I0 constant. Now at this moment, when the source is not able to maintain conduction at the load side, capacitor will take charge and capacitor will discharge into the load, and that's how it will maintain the current I0 constant. Okay, so let us apply KVL on the input side. So if we are going to apply KVL, what we are going to get? So on applying KVL in this circuit, so if we are going to apply KVL, we are going to get Vs minus VL, this is equals to 0, or what I can write here is that VL is equals to Vs, and we know that VL is nothing but L dIL by dt. This is going to be equals to Vs. Okay, or what I can write here is that dIL over dt, this is going to be equal to Vs over L. Now what dIL by dt represent? It represents the rate of change of inductor current, isn't it? dIL by dt is also representing the slope of inductor current, isn't it? Means inductor current is varying linearly, yes or no? And this rate of change that we have calculated is positive. Okay, so this rate of change of inductor current is positive. So what it indicates? The rate of change of inductor current is positive, means derivative is positive. If this derivative is positive, this indicates that the inductor current is increasing linearly, yes or no? This indicates that the inductor current increases linearly. So right now the inductor current is increasing linearly. Now when the inductor current is increasing, half Li square, the energy of the inductor will be increasing, means inductor stores energy at that point of time. So inductors stores energy. Okay, so this is what is happening at this moment of time in this circuit. Let me call this equation 1 and let me call this equation 2. So at the on time, we are having this situation in this circuit. Okay, what is happening at the load end, we will discuss separately. Okay, but one thing is sure, that we have to maintain I naught constant, and who is going to take the task? Capacitor is going to take that task, because load is now disconnected from the source, so source can't maintain conduction there. So the capacitor will be discharging at the load and it will be maintaining I naught constant. Fine. So this is what is happening during the on time. Now let's see what will happen during the off time. So during the off time means now switch will be turned off and diode will be turned on. Now how this is going to happen? Just see here. Now the switch will be turned off. So we have turned off this particular switch. Now the switch is turned off. Okay, now the switch in the circuit is turned off, and let me draw the other components. So right now we are in this situation. Right now we are in this situation. So this is the output voltage, this is the output current, this is the capacitor current, capacitor resistance, and this is our inductor. Okay, now inductor current was flowing in this direction and switch is off. So guys, if the switch is getting off, this is the source current and this is the switch current. If suppose the switch is getting off, that means it is impossible right now to maintain the current across the inductor, yes or no? But you know that current across the inductor cannot change suddenly. Inductor current is in true love, isn't it? With inductor current cannot change suddenly. Inductor loves its current. It cannot be that the current across the inductor is changing suddenly. So it will oppose this change in current. How it is going to oppose this change? In order to oppose this change, what it will do? Earlier the polarity of inductor voltage was like this. So this was the inductor polarity at the beginning. Now inductor will change its polarity and it will reverse its polarity like this. Now due to this polarity of inductor, you can see this diode D will now be in on position, isn't it? And now when the diode will be on, this path is opening up, so IL may become 0, but since diode is now getting on, so IL can conduct in this manner, isn't it? Now IL will be going in this way, IL will be going this way, and it is returning back here, yes or no? So in this way, inductor current can flow in the same direction, and inductor, the energy that it has stored during the on time, it will get ample time to release its energy. So this is what is going to happen in this circuit. When the switch is getting off, diode will turn on and inductor will oppose this change in the circuit, because inductor current is getting equal to 0, which cannot be the case. If you know about inductor, inductor cannot be here that the current across inductor is changing suddenly, isn't it? So what will happen? What will happen? Inductor will oppose this change, and in order to oppose this change, it will change its polarity, and that will lead the diode to be in the on position. Once the diode is getting in the on position, what will happen? If the diode is getting on, IL will get a path and the circuit can now operate, circuit will function, isn't it? Inductor current will get a path to flow. Now it can release the energy what it has stored during the on period. So this is what is happening in this circuit right now. Now if we apply KVL in this outer path, just see this path. If we apply KVL in this path, if we apply KVL in this outer path, inductor, resistance and diode, then what we will get? So on applying KVL right now in the circuit, what we are going to get? On applying KVL, we will get, and what I have told you in the last lectures as well, and I am repeating the same thing. Right now we are having two polarities of inductor. Always go with the reference polarity that you have taken earlier, so that no confusion will get and you will be getting the right things, okay? Unless you have to remember one thing, you have to memorize one thing, that we have reversed the inductor polarity, so that inductor voltage is a -1. Okay, so go with the reference polarity of inductor so that the confusion will not be there. So if you are going to apply KVL, you are going to get VL, you are going to get minus of VL with the reference polarity, minus of VL minus of V naught, this is going to equal to 0, or what we are going to get? We are going to get VL is equals to minus of V naught. Let me call this equation number 3. So what we have obtained here is that VL is equals to minus of V naught. If VL is minus of V naught, that means L dIL by dt, this is equals to minus of V naught, or that means that dIL by dt, that will be equals to minus of V naught by L. Now what dIL by dt represent? It represents the change in inductor current. Okay, it also represents the slope, dIL by dt, derivative of inductor current. And can you see one thing? This derivative of inductor current, this derivative of inductor current is right now negative. So if this derivative of inductor current is negative, now what will happen if this derivative is negative? That means this rate is negative right now. So earlier what we have written here, derivative is positive, now right now the derivative that we have is negative. So if this derivative is negative, that means the slope is negative, that means the inductor current is right now decreasing linearly, isn't it? So what we can say, that inductor current decreases linearly. So right now the inductor current is decreasing linearly. If inductor current is decreasing, the energy that inductor has, half Li square, it also get reduced, means inductor is right now in the mode of releasing the energy. So right now inductor will be releasing the energy. So what we can say, L releases energy right now. So L will be releasing the energy right now. So this is what is happening in this circuit. Let me call this equation number 4. So this is how this circuit is operating right now in on position and in off position. So earlier when switch was on, diode was on, load was disconnected from the source, at that time capacitor is maintaining I naught constant. It was discharging through the load to maintain I naught constant. So since earlier it was discharging, now it is getting a load is getting, now this is getting connected to inductor, isn't it? So now when the inductor current will come, it will take that part of inductor current and it will use it into charging. So right now in this mode, off position, the capacitor will be charging. Earlier it has discharges, now it will be charging. Okay, so this is how this circuit will function. So this is how the circuit is going to operate. This is how the circuit is going to operate. Okay, now let's do the analysis. Inductor voltage and inductor current. So whatever we have obtained, let us plot that. Okay, so if we talk about inductor voltage, what we have calculated for inductor voltage and inductor current, just see inductor current during the on time. Let me call this to be the on time. So this is basically T on. Okay, and what will be this? This will be the off time, or what we can write them, we can also write them d of t, and they can write this to be 1 minus dt, and we know that this is the total time that we have. Now what is the value of inductor voltage during the on and off time? So during the on time, the inductor voltage has a value equals to V of S. So it has a voltage value V of S, and during the off time it is having a value equals to minus of V naught. Now again, if you are going to turn it on, the same pattern it is going to repeat. The same pattern it is going to repeat here. Okay, so this is how inductor voltage is being plotted. This is Vs, and this magnitude that we have is minus of V naught. Now how the inductor current is varying? During the on time, the inductor current is increasing linearly. Okay, inductor current is increasing linearly, and since we have assumed continuous conduction, so current will not be 0 or negative, so it will increase from certain minimum value to maximum value. Okay, and it will decrease from certain maximum value to minimum value. So what you can see, whatever is the value at the starting, the same value we are having at the end as well. Okay, means the inductor current is varying periodically. What was the slope at that time? At that time the slope was Vs over L, and at that time the slope is minus of V naught by L. Okay, so this is how inductor current is going to vary. This is the minimum value of inductor current, and this we will call as the maximum value of inductor current. Now the difference between the maximum and minimum value, it indicates the ripples del IL, and that is called as I max minus I minimum, or we call it ripple current, peak to peak ripple current. Okay, now if we take the average of this current, that will represent the average inductor current. That will represent the average inductor current, and if this is representing the average inductor current, how much amount will be this? So this amount that we will be having is exactly del IL by 2. Okay, so this is how inductor voltage and inductor current can be plotted. Yes or no? Whatever we have obtained through equation 1, 2, 3, 4, we have discussed what is happening in the on position, and we have also discussed what is happening in the off position, and through that, if we are going to plot, this is what we are going to get as inductor voltage and inductor current. Okay, so average inductor current, if we are going to write, how we can write average inductor current? So we can also write the average inductor current, IL average, is all the times I max plus I min divided by 2. Okay, so this is also the IL average value. Okay, and what is del IL? Del IL is basically I max minus I min, and it is called as peak to peak ripple current. This is called as peak to peak ripple current. Del IL is called as peak to peak ripple current. We will be calculating all those quantities later in our discussion. Okay, so this is how what we have obtained during the on time and off time, we have plotted the same here. Okay, now inductor current is varying periodically, isn't it? You can see inductor current is varying periodically, and inductor voltage at that time will be 0, isn't it? What we can write here is that average inductor voltage will be 0. Now average inductor voltage means how do we calculate average of any quantity? Suppose we are calculating VL average, that means 1 upon T for the time period T, VL dt, this has to be calculated, isn't it? Now if we are equating this equals to 0, that means we are equating VL dt equals to 0, isn't it? For one time period. That means whatever is the area it is covering here, that total area will be 0, isn't it? That means that the area is basically 0. Area under the VL curve will be 0. Now how we are going to calculate the area? Area you can calculate, see, this positive area will be Vs into dt. So the positive area will be Vs into dt. Plus, what is this negative area? Negative area will be minus of V naught 1 minus dt. Yes or no? And this has to be equated to 0. Now what we are going to get from here? See, we will be getting dVs. This will go in that side, and it will be V naught 1 minus d. So what we will obtain here is that V naught will be D upon 1 minus D times Vs. And that is the output voltage expression for the BuckBoost converter. This is the output voltage expression for BuckBoost converter. So what expression we have obtained here? We have obtained that output voltage is D upon 1 minus D times Vs. Okay. Now when the duty cycle is in between 0 to 0.5, we will be getting an output voltage less than the input voltage. When the duty cycle is greater than 0.5 and it is less than 1, means it is in this range, we will be getting output voltage greater than the input voltage. So in this moment it will be operating as a buck converter, and in this moment it will be working as a boost converter, isn't it? So what you can see, this circuit can operate as a both. It is boost converter as well and it is buck converter as well. Yes or no, guys? It will be acting as both. It will be a buck converter, it will be a boost converter as well. And this is the expression that we have obtained for output voltage. Okay. So by varying the duty cycle, if duty cycle is in between the range of 0 to 0.5, this circuit will act as a buck converter. It will be giving you an output voltage which is less than the input voltage. If the duty cycle is in between the range of 0.5 to 1, we will be getting output voltage which is greater than the input voltage, means the same circuit will be acting as a boost converter. So right now we don't need separate converter. This alone circuit will be acting as both buck converter and boost converter. So see how important this circuit is and what achievement we have achieved, isn't it? Earlier we have discussed two separate circuits. Now this circuit is doing both the tasks. It is stepping down and it is stepping up the DC voltage at the same time. Yes or no? Depending upon the type of duty ratio that we have. If suppose duty ratio is exactly equals to 0.5, we will be getting output voltage exactly equals to VSS. So this circuit can also operate as a buffer circuit. You will be getting an output voltage and input voltage both equal to each other for a certain value of D to be 0.5. So this is how the things are going to vary in this circuit. Okay. This is how the things are going to vary in this circuit. Now, power balance. Let us apply the power balance right now. So what is power balance? We have assumed that all the devices are ideal. Means whatever is the power input, the same we are getting at the power at the output. Means power input is Vs into Is. Power output will be V naught into I naught. So if suppose I want to calculate I of S, that will be V naught upon Vs into I naught. Now how much will be V naught upon Vs? Right now we have derived an expression. V naught by Vs will be D upon 1 minus D. So what we will be getting is D upon 1 minus D times I naught. So this will be the source current average value. This will be the average value of source current. So whenever you have to find out the source current, this is what you have to do. Whenever you have to find out the source current, this is what you have to do. Source current is always found out through this particular action, power balance. Input power is equals to output power and you will get the desired value of source current. Okay. Now just look into the circuit and can you tell me source current is same inductor current during the on period? Yes or no, guys? Source current and inductor current are same during the on period. Yes or no? What I can write here is the source current is exactly equals to the inductor current for T on equals to dt. During the on time, the source current and inductor current are exactly same. Yes or no? So what we can write here? What we can write here is that if suppose I have to find source, see inductor current is flowing all the time and source current is flowing only during the on time and it is the same inductor current. So if I have to find what will be the source current average value, what will be the average value of source current? So that will be D times the IL average value. Yes or no? Yes or no, guys? This is what we will be getting here. Okay. because source current is same as the inductor current but during the on period. Source current is same inductor current but during the on period. So inductor current is flowing all the time, but the source current is only flowing during the on time, and it is the same inductor current that we have, isn't it? So using this relation, okay, using this relation that we have right now, and what is that relation? We have this relation with us that IS average, source current average value, is basically equals to D times the average value of inductor current. So from here, what will be the average value of inductor current? Average value of inductor current will be the average value of source current divided by D. And what is the average value of source current? That is with us right now. D upon 1 minus D. Let me put the value. D upon 1 minus D times I naught divided by D. So what we are going to get? We are going to get I naught upon 1 minus D. So what is IL average that we have right now? IL average that we have is I naught upon 1 minus D, and this is the same that we have obtained in case of boost converter as well. So in case of BuckBoost Converter and BugBoost Converter, the average value of inductor current is same, isn't it? So this is one of the most important expression that we have obtained. Let me call this to be equation number 3, and then this will be equation number 4, and it will be equation number 5. Okay, so this is one of the most important thing that we have calculated. Average inductor current is basically I naught upon 1 minus D, and the same expression we have obtained in case of boost converter as well. So whether it is boost converter or BuckBoost Converter, average inductor current has the same formula. Okay, so we have calculated two more important things here. Now peak to peak ripple current del IL, let us calculate this value. So this is the inductor current that we have obtained. It is varying from certain minimum value to maximum value, and this is called as peak to peak ripple current. This amount will be del IL by 2, and now what will be this value? This value will be IL average, isn't it? This will be IL average, and what we have calculated for this is I naught upon 1 minus D, isn't it? IL average is I naught upon 1 minus D. Now if suppose we have to calculate peak to peak ripple current, so from equation 2, what we have obtained from equation 2, what was the equation number 2 for us? So equation number 2 that we have calculated, it says that DIL by dt, this is equals to Vs over L. Now DIL represents the change in inductor current, isn't it? So this equation that we have written is for on time, which is equals to dt, isn't it? So during the on time, what is the change in inductor current? Inductor current is changing from I max minimum to maximum. So what is the change? I max minus I min, that is del IL. So change in inductor current is basically del of IL, and this change is happening in what time? So dt will be T on, that is dt, and this will be equals to Vs upon L. So what we are going to get for del IL that we are going to have is Vs upon L into dt, or what we can write for it, that peak to peak ripple current del IL, this will be equals to Vs dVs over F into L. Is the same expression that we have obtained in case of boost converter. So again we have an expression which is similar to the boost converter. In BuckBoost Converter and boost converter, a lot of expressions have similarity. Okay, so what we will be getting here, this will be our equation number 6. So peak to peak ripple current is this quantity. Now what you can see, this peak to peak ripple current is inversely proportional to F and L. They are in the denominator. So if suppose we are increasing the switching frequency, ripple can be minimized, and the purpose of getting a perfect DC, that's what we are using LNC here, averaging networks, will be served. Similarly, if suppose we are increasing the value of L, also del IL will be minimized, and we will be getting minimum amount of ripple, or we will be getting constant DC at the output side. That is the purpose Okay, that is the purpose why we have all these circuits. So this is how we can achieve this. But if suppose you are increasing the inductor size too much, the circuit will become bulky. It will take lot of floor area, cost will increase. Okay, so it should be avoided up to a certain extent. Increasing frequency will be a good thing, and that can be achieved very easily, although we have to compromise with the switching losses, but that can be fine. So this is how the ripples can be minimized. Okay, so we have calculated peak to peak ripple current. Now let us calculate the maximum and minimum value. So what will be the maximum value? I maximum. What will be the I maximum value? Let me write again. What is IL average here? IL average is I naught upon 1 minus D. Okay, so I max, if suppose I have to calculate I max, that will be IL average plus del IL by 2, isn't it? That will be IL average plus del IL by 2. What is IL average? This is I naught upon 1 minus D, and what is del IL? This is equals to D Vs upon FL. Just now we have calculated. Now how we can write this expression? This will be V naught by R. I naught is simply V naught by R, and this is dVs over 2FL. Now we can further simplify it, and what we can do here, V naught can be written as D upon 1 minus D Vs. So this will be equals to dVs upon 1 minus D square into R plus dVs upon 2FL. Or what we can do here, that I max, that will be equals to, we can take dVs as common, and that will be equals to 1 upon 1 minus D square into R plus 1 upon 2FL. So that will be the maximum value. Similarly, we can calculate the minimum value as well. So if suppose you want to calculate minimum value, that will be equals to IL average minus of del IL by 2. So same expression we will be getting, but in between we will be having a negative sign. Same expression is there, but in between we have a negative sign. So this is how we are going to calculate the maximum and the minimum value of inductor current. The maximum and the minimum value of inductor current. Now you may be asked to calculate these current individually. You may be asked to calculate their ratio. You may be asked to calculate their difference. Anything can be asked. Okay, maybe I max and I min you have to calculate, and then you have to calculate IL average. So this is how you can calculate both this current, and finally you can calculate the maximum and minimum values. Okay, so this is how maximum and minimum value of inductor current has to be calculated. Now let us see the role of capacitor. What capacitor will be doing? Capacitor current. So if we are talking about the capacitor current, okay, so you know that inductor is current is varying like this, isn't it? Inductor current is varying like this. Now how is the capacitor current behaving? So just let me take you to the first few slides. Just see here in this circuits what is happening during the on time. So during the on time, the load and source are separated, they are disconnected, and I naught cannot change. I naught has to be maintained constant. So then who is maintaining I naught constant? See, capacitor will be discharging, and it will be maintaining a current I naught here. Okay, so at that time capacitor current will be exactly equals to I naught, but it is flowing in opposite direction. Capacitor is discharging, IC will be equals to minus of I naught. Okay, so IC will be equals to minus of I naught. And during the off time, if you see, during the off time we have I of L, this is equals to I of C plus I naught. Okay, so let me move to the next slide right now. So what do we have during the on time? During the on time, if we talk about T on equals to during T on equals to dt, what is happening at that time? So during T on equals to dt, what do we have? During T on equals to dt, capacitor current is basically equals to minus of I naught, and what capacitor is doing right now, it is discharging. Capacitor discharges across the load to maintain the I naught current constant. Okay, this is how the capacitor will be doing the things during the on time. So what is the capacitor current? It is minus of I naught. Capacitor current during the on time is minus of I naught. It is minus of I naught. Now what will happen to the capacitor current during the off period? So during the off period means during T off equals to 1 minus dt. So during the off period what will happen? So during the off period what do we have is inductor current is basically equals to capacitor current plus I naught, or what we can write here is IC will be equals to IL minus I naught, isn't it? IC will be IL minus I naught. So what we will be getting? This is IL, we have to subtract I naught from here. So we will be getting this kind of figure here. Okay, we will be getting this kind of figure here. Okay, this is what current IC, which is equals to IL minus I naught. Okay, this time we are calling dt, and this time you know is 1 minus dt. And at that time earlier capacitor has discharges because there was no source available, so it has discharges across the load to maintain I naught constant. Now when from the source side we are having inductor current coming as well, so it will take the part of inductor current, it will use that part in charging itself. So capacitor right now charges. So capacitor will charge itself right now. Earlier it has discharges, right now it will be charging. Okay, so it discharges and then it charges. This is how it will be behaving. Okay, now during the charging and discharging there will be some trapped charge carriers. Okay, so what is the charge stored during that particular time? So if suppose we want to calculate del q, if suppose we want to calculate what will be the value of del of q, what will be the value of del of q? So how we are going to calculate that? So in order to calculate del q, just see here, del q, charge trapped during the on or off period, this is equals to the area. Yes or no? How much is the area? Area is basically I naught into dt, or what we can write for del q is it is C times del Vc or del V naught. This will be equals to I naught into dt, or what we can write for del V naught, this will be equals to I naught dt upon C. Okay, so this is the expression for del V naught that we have. This is the expression for del V naught that we have. And what do we call del V naught? Del V naught is nothing but peak to peak ripple voltage. This is called as peak to peak ripple voltage, isn't it? This is called as peak to peak ripple voltage. And what you can see here, that in this expression we have capacitor C in denominator, and what we have assumed that we will be taking the capacitor value to be very high so that the ripple in the output voltage can be minimized and output voltage can be maintained constant, isn't it? So you can see here, if we choose the value of capacitance to be very high, this ripple can be minimized and the purpose of getting perfect DC at the load can be achieved. Okay, but there are cons for this particular thing. If suppose we are taking the capacitor to be too much high, it will increase the overall size, isn't it? And the solution for that is interleaving of the converters, means we will be connecting 2 or 3 or more than 2 or 3 converters in parallel, and that's how we can reduce the size of capacitor. Okay, but that's a different topic. Okay, just don't go into that right now, focus here. If capacitor value is very high, we can minimize the ripples in the output voltage. Okay, now again what I would like to note you here, that we have obtained del V naught, and which is equals to I naught dt over C. I can also write this expression to be I naught, I can write V naught by R into D, and T I can write F. Okay, now guys, if suppose del V naught upon V naught I am calculating, then this will be equals to what? This will be equals to D upon RCF. Now nobody is going to teach you this particular thing. Okay, and this is only you will be getting at IMS GATE Academy. Now this is called as percentage ripples. Okay, this is called as percentage ripple in output voltage. percentage ripple in output voltage. So if suppose it has never been asked in GATE exam, but in the upcoming GATE exam this can be asked. So this is what you have to calculate, not del V naught. Okay, del V naught is not you have to calculate. You have to calculate del V naught upon V naught. This is called as percentage ripple in output voltage. So this is how the behavior of capacitor and the things related to capacitors can be calculated. Now which number of equation this will be? So earlier we had equation number 6. Let me call these both to be the equation number 7, and then this equation that we have will be equation number 8, and let me call this to be equation number 9. Okay. After that, after capacitor current, let us calculate the switch current and the diode current. Okay. So this is how inductor current is behaving. Yes or no? If we are talking about the switch, isn't it? So switch is there at the source side, inductor is in between. Now switch current is flowing during the on time, and it is the same inductor current during the on time, isn't it? So switch current will be flowing, switch is on during the on time. So when switch is on, switch current will be flowing, and at that time the switch current is nothing but it is the same inductor current. So whatever is the inductor current during the on time, it will be having the same shape. Good evening, Nikhil. Welcome to IMS GATE Academy. So whatever is the shape of inductor current, switch current will be having the same shape during the on time, and during the off time, as the switch is in off condition, there will not be any switch current. Yes or no? So if we want to draw this current, how we are going to draw it? Just see here. Whatever is the shape of inductor current, the switch current will be having the same shape during the on time, and during the off time it will not be there because the switch is turned off. So this is how the switch current will be behaving, or this is how the switch current waveform will be. Now this I will be calling as the average switch current. This I will be calling as average switch current. What is this? This is average inductor current. And how much is this? I naught upon 1 minus D. So this is how the switch current can be obtained. Now when it comes to diode current, you know that diode is turned on during the off period, and what current it is carrying at that time? Diode is turned on during the off period, and at that time it is carrying the same inductor current. So whatever is the inductor current shape during the off time, it will be having the same shape. During the on time, it has no appearance, it was off, isn't it? So during the on time, it will be having a value equals to 0. During the on time, it will be having a value equal to 0, but during the off time, it will be having the same shape as the inductor current has. So this is how we are going to draw the diode current, and let me call this to be the average diode current. Okay. Now it's time to calculate this value. So what do we call this time? dt. And what do we call this time? This is 1 minus dt. So how we are going to calculate their average value? Just see here. It's very easy. If suppose we have to calculate the average switch current. Average switch current. So what you can see here? Switch current is only flowing during the on time, and in that time it is the same inductor current. So it might be calculated in the proportion of inductor current. So this will be equals to D times the average inductor current, and you know that average inductor current is what? I naught upon 1 minus D. So this will be D upon 1 minus D times I naught. So this is how switch current can be calculated. Similarly, if suppose you want to calculate the average diode current, then in order to find the average diode current, what you can see here is diode current is present only during the off time, and it is the same inductor current. So it must be calculated in the proportion of inductor current. So that will be equals to what? During the off time means 1 minus D times IL average. Once you are putting the value of IL average, and what is the value of IL average? It is I naught upon 1 minus D. So what you are going to get? You are going to get I naught. So what is ID average? ID average is basically equals to I naught. Okay. The same values we have obtained in case of boost converter as well. So boost converter and buck boost converter, they have a lot of similarities. Lot of formulas are exactly equal to each other. Okay. So this is how we can calculate the different switch currents. And this is going to be what? Which number of equation? 8, 9 we have, and this is going to be equation number 10 and equation number 11. So this is how we have calculated different currents in this circuit. So all the currents right now are with us. Now after that critical inductance. So what will be critical inductance? So as we have discussed in boost converter and buck boost converter, sorry, boost and buck converter, inductor current is what we have assumed here is continuous. Okay. It may be continuous if inductor is able to sustain the energy for a particular time of duration, whom we are calling on time and off time. If suppose inductor is having value less than certain critical value of inductance, it will not be able to sustain that energy for dt times and 1 minus dt times. It may release its energy even before, and at that time, if the energy is released, the inductor current may fall to 0 or it may become negative as well, and that conduction is now become discontinuous. Okay. So there should be a minimum value of inductor in the circuit. So we will be choosing inductor to be greater than that particular minimum value, so that the assumption of having continuous conduction can be maintained. Okay. So if continuous conduction is there, that means if suppose I minimum is always greater than 0, means if it is positive, then we have assured continuous conduction mode. If I minimum is less than 0, means it is negative, then it is guaranteed that the mode in which we are operating is discontinuous conduction mode. So what is the boundary between two? If suppose we are talking that I minimum is approximately close to 0, then we are at the boundary of CCM and DCM, continuous conduction mode and discontinuous conduction mode, isn't it? So what is this critical inductance? All these are related to that. The circuit must have a critical value of inductance so that continuous conduction can be assured. If the inductor that we have in the circuit is below a certain critical value, discontinuous conduction will be there, and that is not desired. Okay. We want the current in the circuit to appear all the time. So what is this critical inductance? It is the minimum value of inductance that the circuit should have so that continuous conduction can be assured. Okay. So what condition we are having for continuous conduction? Critical inductance. If we are talking about the critical inductance, what definition we can write for it? We can write a definition for critical inductance, and which will be, it is the minimum value of inductance for which the circuit is operating at the boundary of continuous conduction mode CCM and discontinuous conduction mode DCM. That is, one thing is assured, I minimum is close to 0. It is neither negative or neither it is equal to 0. It is quite close to 0. So if we are doing this thing, that means we are calculating IL average minus del IL by 2 equal to 0, or what we can write here is that IL average that will be equals to del IL by 2. So this is an important condition that we have obtained. Now looking into this condition, we can have an expression here. IL average is basically I naught upon 1 minus D. Now this is equals to del IL, which is D Vs upon FL, and L will become LC right now. Now I naught can be written as V naught by R, and V naught can be written as dVs upon 1 minus D. So finally we can write this to be like this. Okay, now this is dVs upon 2f LC. Now this get cancelled, and what will be having for LC? We will be having LC value as 1 minus d square r by 2f. So this is the formula for critical inductance that we will be having. Now we have to choose the value of inductance in the circuits to be greater than this value unless the continuous conduction cannot be assured. Okay, if the inductance is having a value less than this value, then the circuit will be operating in discontinuous mode. So if you want to ensure continuous conduction, critical inductance or the inductance of the circuit must be chosen greater or equal to this inductance. Okay, so this is how we will be calculating critical inductance. Okay, now after that, critical capacitance. So in the same way as we have derived a condition for critical inductance, same way we can write that V naught average, this will be equals to del of Vc or del of V naught by 2. So what is V naught average? We can write it I naught into R. What is d of V naught? See, we have calculated one expression for it. What is del V naught? Right now we have calculated. What is del V naught? Del V naught is basically I naught dt upon C. Okay, I naught dt upon C. I naught dt upon C. Now C will become Cc here. I naught and I naught get cancelled, and what will be the value of Cc? Cc value that we will be having is d upon 2 Fr. Now that will be the value of critical capacitance that we will be having here. Okay, so this is it. We have calculated each and every parameter of the circuit. We have discussed its operation. Okay, and I don't think there is any problem that you people have faced here. So now what are the important expressions that we have calculated? We have calculated that average output voltage is d upon 1 minus d times Vs. Okay, in fact I have to write it modulus of V, this is equals to d upon 1 minus d times Vs. Okay, because the kind of polarity we have taken, if suppose we are taking like this type of polarity, the output voltage that we will be getting is positive. Okay, but if suppose we are taking this polarity, the output voltage that we will be getting is negative. And we are free to choose any type of polarity at the output voltage. So better to write modulus here. Okay, but the overall formula will be the same. So depending upon the polarity, you will choose a sign. If suppose you have this polarity, you will choose positive sign. If you have this polarity, you will choose a negative sign in between, negative sign before this formula. After that, what is the important expression that we have? This is the output voltage expression. And after that, we have a peak to peak ripple current expression, which was equals to d Vs over Fl. Okay. What is IL average? Inductor current. Average inductor current is I naught upon 1 minus d, or finally it can be written as dVs upon 1 minus d square into R. This is the average inductor current. What is average switch current? Average switch current was d upon 1 minus d times I naught. What is average diode current? Average diode current that we have is equals to what? I naught. What is average source current? Average source current is related to average output current in the same manner as the input and output voltage are related to each other. Okay. Now what is the average critical capacitance expression? This is 1 minus d square R by 2f. Okay. And after that, what do we have as voltage ripple? Del V naught. So what is del V naught? It is I naught dt upon C. Okay. And if suppose we have to calculate del V naught upon Vt, V naught, del V naught upon V naught, how much this will become? This will become d upon FRC. Okay. This is called as percentage output ripple. Very important expression. And then we have finally expression for critical capacitance, which is d upon 2FR. Okay. So all these are the important expression that we have. Good evening, Neha. So all these are the important expression that we have related to BuckBoost Converter, and we have calculated all of them. Okay. Do not put any effort. Good evening, Stuti. Do not put any effort in memorizing these expressions, guys. Just put your efforts on practicing this circuit, because anytime, whenever, whatever is required, you can calculate at the same time. So why to pressurize yourself in remembering so many formula? Since there is not only one converter, we have three converters: buck converter, boost converter, buck boost converter. If you are going to remember or going to memorize all the formula, you will mess up with them. So better to just practice the circuit and calculate the expression whatever is required whenever is required. Okay, fine. Now let's apply this learning that we have into the gate problem. So see, let us practice few gate problem. Can you see this question? This was a part of GATE 2022 exam, and what has been asked here in this question? Just read this question with me. The steady state current flowing through the inductor of a DC to DC buck-boost converter is given in the figure below. So we have the inductor current being given to us. If the peak to peak ripple current in the output voltage, if the peak to peak ripple in the output voltage of the converter is 1 volt, okay, then what will be the value of output capacitor that we will be having? So this is the current that we have been given. Okay, so inductor current is given. This is what we are calling I minimum, and this is what we are calling as I maximum. So guys, if I minimum and I maximum is given, we can calculate what will be IL average. How much will be IL average? IL average will be basically I max plus I min divided by 2. This is 12, this is 16. So 12 plus 16 by 2. 28 by 2 or 14 ampere is what we will be having here. Okay. 14 ampere is what we will be having here. Now, what else has been given is the peak to peak output voltage ripple, and that is equals to what? That is equals to 1 volt. And what we have to calculate? We have to calculate what will be the value of capacitor. So capacitor is something that is we have to calculate. Do you remember the capacitor current waveform? The capacitor current waveform was like this, isn't it? The capacitor current waveform was like this. Just see here how we can easily derive the expression. We don't have to put any effort in memorizing them. So just see here how easily we can get the expression. This was the capacitor current expression. Yes or no? This was current I naught. Okay. So this one is the charge trapped. So what was the charge trap? I am again deriving the formula. Del Q, that will be equals to I naught. This time is dt and this time is 1 minus dt. So I naught into dt. Now what we can write here is C del V naught. This is equals to I naught into dt. Okay. Now what is del V naught? Del V naught is I naught, and what we can write dt? Dt is nothing but the on time upon C. Why I am writing this to be on time? Because on time is given to us. What is on time? On time is 20 milliseconds, isn't it? Microseconds, sorry. On time is basically 20 microseconds. On time is 20 microseconds. And what is off time? Off time is also given 30 microseconds. So we can simply put the values here. So off time and on time, just put the values here. How much we will be getting? And it is required to calculate the value of C. So better we write this expression in terms of C instead of del V naught. So if suppose we want to calculate C, that will be equals to I naught into dt. We can write T on divided by del V naught. Now I naught, how much is T on? T on is basically 20 microseconds, means 20 into 10 to the power minus 6. Del V naught is 1. So capacitor value will be 20 times I naught into 10 to the power minus 6. Okay. So guys, what we have to calculate is right now I naught. So I naught is what we are required to calculate, and I naught, you know, will be equals to what? IL into 1 minus D. Yes or no? Because this is the inductor current waveform which is given to us. If I am going to calculate the average value here, then IL average will be what? IL average in case of boost converter and buck boost converter is I naught upon 1 minus D. So I can write the value of I naught to be IL into 1 minus D. Okay. What is IL? IL we have calculated as 14 ampere and 1 minus D. 1 minus D. What will be the value of D? What will be the value of D? Just see here. The value of D will be T on divided by total T. Okay, so how much is T on? 20, and how much is T? 50. So what we will be getting? 2 by 5 or 0.4, isn't it? 2 by 5 or 0.4. So D value that we have is 0.4. So how much we will be getting? 14 into 0.6, that is 8.4 ampere. Just come here and put the value 8.4 into 10 to the power minus 6. That will give you 168 microfarad. Okay. So this is how we can simply calculate this answer. We can simply solve this question. And I don't think that you are having any problem, isn't it? So this is how we can recall the facts. We can derive the particular formula required without pressurizing ourselves, isn't it? So this is how you could have approached for this problem. This was having 2 marks attached with it, and it was too easy to score those marks. Let me move to the next problem. Now this was a part of 2021. So regularly there was question from boost converter. This year, in the upcoming year 2024, surely you are going to get a question from boost converter. What has been said in this question is, consider the buck boost converter shown. So this is the buck boost converter that we have. Switch is operating at 25 kilohertz. What is given? 25 kilohertz means F is given 25 kilohertz. Fine. And duty cycle is 0.75. So at 0.75 it will be acting as a boost converter. Assume diode and switch to be ideal. Under steady state condition, the average current flowing through the inductor will be. What we have to calculate here is, average inductor current. Okay. So in order to calculate average inductor current, what do we require? We require the value of I naught upon 1 minus D. So D is with us, isn't it? I naught we don't have. I naught we can calculate by V naught by R. Just see here how easily I am going to derive all the formula. So V naught in case of buck boost converter, you know V naught is equals to D upon 1 minus D times Vs. If I am going to put this value, I am going to get dVs upon 1 minus D square into R. Okay. D is with us. How much is D? 0.75. Vs is 20 upon 1 minus 0.75 square into what is R? 10. How much we are going to get? How much we are going to get here? Tell me guys, how much we are going to get? This will give us 2, and finally you will be getting 600 by 25. So it will be 2. How much you are going to get as answer? Just let me know. This will be 2. 0.25 will give us 3. 2 into 3 will be 6. 6 upon 0.25. How much is 6 upon 25? 600 upon 25. 25 into 2 is 50. Okay, and apart from that 24. So I will be having an answer as 24. Okay. So 24 will be the correct answer. So can you see here? Is there any problem that we are having in this problem? I don't think so, isn't it? So this is how simply you can solve this question. Average current is flowing through the inductor is required. Nice. This question is having 2 marks, yeah. So it is very easy to score in these topics. Okay. And buck boost converter, DC to DC converter are surely going to give you 2 to 4 marks of questions. Okay. So just follow all these 3 lectures of mine that I took on buck converter, boost converter, and this is going on buck boost converter, and nobody can stop you scoring marks out of this particular topic. Okay. Now let us move to the next question. This was a part of GATE 2017, and what has been said here, in the circuit shown all elements are ideal and the switch S is operated at 10 kilohertz. circuit is basically BuckBoost Converter. So what is the frequency? Frequency is 10 kilohertz. Just write the data what has been given to us. Duty cycle is 60%, that means 0.6. The capacitor is large enough so that the ripple across it is negligible. Okay, this is the best line. If it is written, we are completely free. Okay, across it is negligible and a steady state requires a voltage as shown. Output voltage is how much? 75 volt. Okay, whatever is the voltage here, the same voltage will be here because they are connected in parallel. So output voltage and the polarity, can you see the polarity? The polarity is like this. This is plus, this is minus. So this output voltage that we will be having is positive and it is given 75 voltage. In some cases the polarity is given just reverse of it. In that case output voltage you will be taking as negative. Okay. The peak current in ampere drawn from 50 volt source will be, okay, 50 volt source. So this is the source. Now what will be the peak current drawn by this source? Okay, peak current drawn by the source. So we have to calculate the peak current of the source. Now let me ask you one question. When will be the current flowing across the switch? When the switch will be on, only then the current will be flowing, and at that time the current that the switch is having exactly equals to the same inductor current. So we don't have to calculate source current maximum value. In fact, we have to calculate inductor current maximum value. Whatever is the maximum value of inductor current, the same value the source will be having. So peak value of source current that we have to calculate is nothing. The peak value of source current that we have to calculate here is nothing but the peak value of inductor current, and that is called as I of max. Okay. So guys, if suppose we want to calculate the peak current of source or I max, then you know that this is equals to IL average plus del IL by 2. Okay, IL average plus del IL by 2. Now put the values here. This will be I naught upon 1 minus D, and this will be D Vs upon F into L. All the data is given to us. Just put the values. I naught. If suppose I have to calculate I naught, how I can calculate I naught? Just see here, the output voltage that we will be having here is 75 volt. So what will be I naught? I naught will be 75 divided by 5, that is 15 ampere. Yes or no? So just put the values here. I naught that we will be having is 15 ampere upon 1 minus D is 0.6 plus D is 0.6, Vs is 50 divided by 2 into F that we have is 10 kilohertz and L might be in millihenry. Yes, 0.6 millihenry that we have. How much we are going to get? This is 15 divided by 0.4, and what we'll be getting here? Just see, 0.6 get cancelled, 10 to the power 3 and minus 3 will be resolved. We have 50 upon 20 here. So 50 upon 20 is how much? 50 upon 20 is how much? Or we have 5 2 by 2, that is 2.5 here. Okay, so how much we are going to get here? Just let me know. 15 by 0.4 will be what? 37.5 plus 2.5, and that is equals to 40 ampere. Now what else is required? What is the problem? Why one can't solve this question? I don't have any reason, isn't it? This is the easiest of the problem. What you have to do? You have to apply simply all the rules and regulations. If suppose you have the circuit with us, and circuit is almost all the cases it will be given to you. You can pretty easily find the things, isn't it? And in this problem, they have just tried to confuse you with the peak value. Okay, they have just tried to confuse you with the peak value. They have written some peak kind of things and students were confused what they have to do. So guys, this is how you can solve this question very easily. Okay, let me move to the next question. Now focus on this. This was a part of GATE 2016 and it is my favorite one. So what has been given in this question? A BuckBoost DC to DC converter shown in the figure below is used to convert 24 volt is used to convert 24 volt battery voltage to 36 volt DC. So input voltage Vs is given, output voltage V0 is given. Okay, if this is 36 volt, the same we will be having across the capacitor as well. To feed a load of 72 ohm, it is operated at 20 kilohertz with an inductor of 2 millihenry and output capacitor of 1000 microfarad. All devices are considered to be ideal. The peak voltage across the solid state switch will be. So what will be the peak voltage across the switch? Let me call this switch voltage to be VSW. And how we are going to take the inductor polarity? This is how we are going to take the inductor polarity. Okay. Now in this circuit, when the switch is on, what will happen? If the switch is in on position, at that time the drop across the switch will be 0. So switch voltage will be 0 at that time. When the switch will be off, only then it will be having some voltage across it, isn't it? When it is on, the drop across it will almost equals to 0. What will be the voltage across it? That we will be having some voltage across it during the off position. So if simply we apply KVL during the off position, now in this time VSW will not be 0. If we apply simply the KVL here, what we are going to get? Vs minus VSW minus VL, that is equals to 0, or VSW that we will be having is Vs minus VL. How much is Vs? 24 volt minus. How much is VL? This voltage and this voltage is exactly equals to each other, isn't it? So how much will be VL here? VL will be minus of 36 volt. So let me put the values. So if I put here minus 36 volt, I am going to get 60 volt as answer. Now so many students have answered 12 volt and that is wrong. Okay, very good Nikhil, well done. Okay, so this is how we will be getting an answer. Switch voltage will be 60 volt. Now this is a gate question, isn't it? This is a gate question. And can you see how easily we have solved and scored 2 marks? The same you will be doing in the year 2024 as well. Just keep on following IMS GATE Academy. Okay. Now let me move to the new question. Now this is not from BuckBoost Converter. Since this is the last lecture from DC to DC converter, so I have taken this particular problem, a mixed bag question. This is related to buck converter. In the year 2018, this question has been asked. And what is given in this question is, the figure shows 2 buck converters. So you can see 2 buck converters are connected in parallel to each other. Why we are doing so? Why we are connecting 2 buck converters in parallel to each other? Normally guys, we are taking the size of capacitors to be very high so that the output voltage and the ripple can be minimized. By taking the capacitor size to be very high, overall size of the filter will increase, isn't it? And that is not a good thing. How we can just remove this particular disadvantage? By interleaving the converters. Interleaving means connecting the converters in parallel to each other. So what you can see here, we have connected 2 buck converter in parallel. So what will happen? The overall ripple reaching here will already get minimized. So if the ripple is already getting minimized by the circuit operation, we will be needing a very less value of capacitor, low value of capacitor. So that particular disadvantage is now will be removed if we are having this particular kind of circuit. Okay, so that's the purpose of doing interleaving or connecting converters in parallel. Okay, forget it. So this is the circuit that we have. 2 converters are connected in parallel. Now what has been said here? The common input DC voltage for the converter has a value of 100 volt. So Vs is given 100 volt. The converters have inductor of identical value, fine. The load resistance is 1 ohm, also fine. The capacitor voltage has negligible ripples. That has to be the case because we have connected converters in parallel. Both converter operates in continuous conduction mode. The switching frequency is 1 kilohertz. Okay, so what do we have? Switching frequency is 1 kilohertz. Let me write here. Switching frequency is 1 kilohertz. And the switch control signals are also given. So switch control signals are also given. Now we will be calling this to be the on time, okay, and we will be calling this to be the off time. Yes or no? Isn't it? So what will be the duty ratio? duty ratio will be on time divided by the total time. So on time is 0.5, okay, and total time is 1. So duty ratio will be 0.5. So this is how you will calculate the duty ratio very easily. Now what else we have to do? The circuit operates in the steady state assuming that the converters share the load equally. Average value of IS1 across the switch 1 will be what? We have to calculate what will be the IS1 current, okay? What will be the IS1 current? This is what we have to calculate here, okay? This is what we have to calculate here. So just see here, source is giving current I of S, and this current is getting divided into these two converters which are identical, yes or no? So what will be I of S1 or I of S2? They are identical, so they will be equals to IS upon 2. So what we need to find here is IS current. If suppose we get the value of source current, we will be able to calculate any of these currents. So what will be the value of source current? What will be the value of source current? So this is what? This is buck converter. So in case of buck converter, what is the value of source current? This is equals to D times I naught. Okay, this is equals to D times I naught. Now I naught is not directly given to us. So what we can write? We can write D times V naught upon R. And what is dV naught? What is dV naught? V naught can be written as D times Vs, okay, upon R. So finally it will become D square Vs upon R. Now everything is given to us. This is 0.5 square into Vs is 100 divided by resistance is 1. How much we are going to get? 25 ampere. So if they are 25, any of these currents, whether it is IS1 or whether it is IS2, they will be 25 by 2 and that will be 12.5 ampere. This is how we can solve this problem very easily, okay? So this was a very good one. It was there in the exam in 2018. Now this kind of questions, this kind of question in which two converters are parallel. Right now we are having buck converter parallel. In future you can have a question related to boost converter getting connected in parallel, buck boost converter getting connected in parallel. They may be repeated. So this is how you have to process, okay? So this is the end of this lecture, boost converter. Now in this series we have completed buck converter, boost converter, buck boost converter. These 3 lectures, watch them as many times as you can, okay? Only these 3 lectures are very important for you, because the weightage of DC to DC converter in the exam is around 2 to 4 marks. You can have at least 2 marks question, or you can have maximum of 4 marks of question. On an average you will be getting a 4 marks of question from this particular topic as well, and these 3 lectures will surely help you in getting those marks, okay? And that's the purpose of IMS GATE Academy. In order to explore more about our content, our material, our teaching style, and more about IMS GATE Academy, the description box is having all the details. So through that you can contact us, you can join us, join our zero fee program, you can join our Telegram group, and you can explore all the things that we are offering here, okay? And then you can finally make up your mind to join us finally. So that's the end of this lecture, guys. Now in the next lecture, that is going to be held on the upcoming Thursday, we will be covering very important topic, single phase inverters, and I will be dealing single phase half bridge inverter, single phase full bridge inverter, and all the details, all the hidden concept and all the obvious concept, all the stated and unstated concept I will be discussing there, okay? So thank you for attending this session. Thank you for watching this session. I will be live again on Thursday with this topic. So I will be waiting for you guys there. Thank you. Thank you so much.